second group. Maybe the second group.
Yeah. Let's do like next week, basically.
The 20th.
It's the 20th.
Something like that, right? First. Something or something like that.
This is the 21st.
Like early 20th. That's right.
I really need to look at it.
He hasn't been here since, right?
No. Like, I haven't seen him in,
I know you said it's just
he wasn't even here for the exam, so. Yes, I think he just dropped. Because like he'd be bombing these class because he grades attendance. You have like 3. You can miss class like 3 times.
Okay, so last week was all about the normal distribution,
Like
right?
absence,
We looked at standard normal
right?
and the regular normal. So what we're going to look at now is a distribution of certain statistics, specifically means and proportions. This is the central limit theorem. I'll even through that. We have sampling error whenever we sample. Right, so obviously whenever you take a sample to approximate some kind of value, there's going to be error associated with that. And this is our sampling error. If you're given a random variable x, x bar is the sampling distribution of the means. Right, so generally speaking, what we do is we have, don't want to say a population, but we have a set of data. We take random samples of a certain size from that data. Calculate the mean. Rerun that experiment. Calculate the mean. Rerun that experiment. Calculate the mean. That is what the distribution of sample means is. The larger your sample size, the smaller the sampling error tends to be. So the question is, we run that experiment several times. So again, you take a sample size of, let's say, 500. You calculate the mean, and then you do another sample size of 500. Calculate the mean. You do another sample size of 500. Calculate the mean. Keep going. How are those means distributed? That's what we want to look at. So given the variable x and a sample size of n, there are 3 cases that we examine. First case is x is already normally distributed. If that's the case, then x bar will be normally distributed, regardless of your sample size. However, generally speaking, your population is not normally distributed, and it's very rare that a population is perfectly normal. So what we use is we use what's known as the central limit theorem. And this is a pretty important theorem. In fact, this theorem is going to be used in all of inferential statistics. There are two versions that we look at. There's the one for mean and the one for proportion. Here's the one for mean. If you have a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the population from which it came. Obviously, the approximation becomes better as you increase your sample size. Until theoretically, this can use a little bit of calculus, if you let n approach infinity, then x bar will be perfectly normal. It's fine. Let's say it. What do we mean by large? We usually take n to be no less than 30. So this end, let's look at this graph. So this graph is giving us a population. This histogram represents some population, and we can see it is definitely not normal. In fact, it is very right skewed. Right? The next graph that we're going to look at is a histogram where we calculated the means from that population of sample size 3. Right, so all of the possible samples of size 3, all of their means. Still right skewed. Although a little less, right? Well, graph C is going to be same thing. We're going to take samples, calculate all the possible means, but this time size 10. Still not quite normal, but notice the skew is a lot less now. Now let's increase the samples to 30. That's pretty close. So it's safe to assume normality. Which leads us to the second case. If your sample sizes are 30 or more, then we can take x bar to be approximately normal, regardless of how x is distributed. So if x is already normal, doesn't matter what your sample size is. If x is not normal, you need a sample size of no less than 30. Then we can approximate x bar as normal. If x is not normally distributed, and our sample size is less than 30, there is nothing we can do in this course. All right, so now let's say we know that X bar is either normal or approximately normal. What are the test statistics? Not test statistics, sorry, the statistics. All right, so remember, normal distribution has two values: mean and standard deviation. All right, so the question is, what is the mean of the means? What is the standard deviation of the means? So mean of the means, just use of X bar. And what we find is it's just the population mean. Standard deviation of the means, sigma sub X bar. It's the population standard deviation divided by the square root of n. Again, n is the sample sizes. This is also called the standard error. So we're given a random variable x, has population mean, mu, standard deviation, sigma. If x bar is normally distributed, so if x is normally distributed, we proceed. If the sample sizes were 30 or more, we proceed. Otherwise, there's nothing we can do. Calculate your mean. Well, it's just the population mean, so that's really easy. Calculate your standard error. Then we can proceed with the problem. All right, so we'd say that x bar is normally distributed, mean mu of x bar, and standard deviation of sigma x bar. And then this is going back. If you're calculating by hand, you're going to standardize it, right? So you have your z-score, and it's the same. It's just now you have a different mean and a different standard deviation. The x bar here doesn't represent a mean from the random variable, right? That x bar is a value of the random variable, because that random variable is means. If I go back, this is probably so you need that. That's the important bit, and on the previous slide it was x being normally distributed or sample size being large. So that was essentially the whole takeaway of that. Oops. course, we already know z-score. So battery lifetimes can be modeled as a normal distribution. Simple random sample of n equals 36. Find the probability that the mean of that random sample is larger than 41. Well, it's already normally distributed, so the sample size doesn't even matter. We know that the distribution of means is also normal. The mean of the means is just the population mean. What is the mean of X? It is given. Look at the wrong one. It's 40. Remember, it's always written this way. Mean, comma, standard deviation. So that one's easy. Now we want the standard error. That is your standard deviation divided by square root of the sample size. What is standard deviation? What is the sample size? What's the square root of 36? So standard error would be 5/6. .83 repeating. So let's just go to 4, go to 0.8333. So that's what we can say. X bar is normally distributed with a mean of 40 and a standard deviation of 0.8333. Now we can answer the question. What is the probability X bar is larger than 41? Well, we want to convert it to standard normal. Let's do this. 41 minus 40 is 1. 1 divided by standard error, well, I know standard error is 5/6. That'd be 6/5. 1.2. It's probably right about there. It's looking for greater than, right? So what area are we looking at? Area to the left or area to the right? We want area to the right. But that is not what our table gives us, is it? The table gives us area to the left. So how are we going to find that desired area? Don't care. Why did that change? Why that changed? Right, so we need to come down to what, 1.20 on the z-score, right? That's a nice and easy one. Right, 0.8849. That's going to be what? 1.151. Just make sure I read that. 0.8849. Weekly study time, right skewed, with mean 8.4, standard deviation of 2.7 hours. Random sample of 45 is selected. What is the probability that the average study time is between 8 and 9 hours? First thing, is the population normally distributed? No. Is the sample size large enough? It is. What's the smallest sample size it needs to be? 30. Sample size is 45. So we can assume normal distribution. What does its mean? 8.4. Its standard deviation. Divided by root 45, right? And what's that going to give us? Let's go out to 4 decimal places. 5. I believe I specified. Yeah, I think I specify how many to use for the test. I'm used to using 4, so I'm just going to use 4 for everything. We have to standardize it, right? Because we're reading this from a table. I'm not going to write out the standardization this time. It's going to be 8 minus 8.4, then divided by that 0.4025. Z-squares will only go to 2 because that is all our table gives us. So we can use negative 0.99. and 1.49 is the upper limit. The area we're looking for is in between, right? Be that. But again, that is not what the table gives us. How did we find probabilities between two values? What did we do? The z table only gives us area to the left, right? How did we find an area between the two values? We're going to take the difference, right? Looking for negative 0.99 and 1.49. Let's start with the 1.49. We're at 0.9319. Negative 0.99. There's negative 0.9. .1611. that difference. Seven, zero, it should be right. So heights can be modeled as a normal distribution for a sample size, a random sample of 25. Compute the probability that the average height is between 66 and 68. Can we assume H bar is normal?
No,
Why do you say no?
because it's 25.
What was the other condition for it to be normal? Either your sample size is large enough, or what about the original population?
Even distributed.
Wow. What do you mean by evenly distributed?
Do not continue? No.
So there's two highlighted. Large enough sample size or what?
X being normally distributed?
So the population being normally distributed. What do they tell us about the heights? Heights are normal. Since the population is already normally distributed, their means are normally distributed.
Wait, why is the height like normal? Because it's like 66, 67, 68? Or that?
No, that's the probability that the average height of this sample size will be between 66 and 68.
Oh, okay.
What I have highlighted is the population heights. And that says normally distributed with a mean of 67 and a standard deviation of 3.1. That's what that notation means.
Okay.
So the mean of the average heights is the same as the mean height, so just 67. Our standard error (3.1 over 25). So let's take oh, that's nice. 0.62. We want this probability. This one we're going to read it from the calculator. And so we did 2 by hand. We'll do a couple by calculator. You will still need to calculate the mean and standard error. Because now we're just going to use the normal distribution like we did last time. Right? Normal CDF. Lower bound was 66. Upper bound was 68. The mean was 67. The standard deviation, what we said was 0.62. That's a probability of 0.8932. And it should go without saying, right, that you should practice getting these values on your calculator. Make sure you know how to do it. Test score is normally distributed, mean score of 78, standard deviation of 10. For n equals 16, find the value of c so that the probability of x bar less than or equal to c is equal to 0.90. Well, isn't that the 90th percentile of mean scores? Is x bar normal? Is the population normal? No.
No. For normal.
Population is normal. They tell us that. Test scores are normally distributed. Which makes x bar normal, regardless of sample size. Average test score 78, so that is the average of the means. Standard error, standard deviation, which is what, 10, divided by square root of the sample size, which is 16, isn't it? Square root of 16. Or, that's a nice one to work with. 10 over 4. It's 2.5. So the 90th percentile remember, this time we want the inverse normal. Because they give us the area. 0.90, right? 90th percentile, 0.9 area to the left. 78 is the average. .5 is the standard deviation. Let's just stick with no decimal places. Say an average test score of 81, average of 81.
If we really use decimal points, would it be wrong? If we use the decimal points, would it be wrong? Or okay, just because test score keep it like.
Yeah, it wouldn't be wrong. Unless I told you not to use them in the problem.
Okay.
All right, what does that mean? 90% of the averages are below 81. Because remember, what we're doing is we're taking all the test scores, we're finding all samples of size 16 and calculating the means of all those samples. That's our distribution. I think that's what your project's asking you to do. Both for means and proportions. X is normally distributed. Mean 100, standard deviation of 15. Sample size of 36 is being used. Compute the probability that X bar is less than or equal to 104. I shouldn't do this totally with Excel. So they already told us it's normally distributed, so we can do this. Normal distribution. The value we wanted to be less than or equal to was 1 over 4, wasn't it? We need the mean, which is just the mean of the population 100. We need standard error. This is, it should allow me to do this. Standard deviation of the population, which they told us was 15, divided by square root of the sample size, 36. So I don't need to do a separate calculation for that, I don't believe. We'll find out if this gives me an error. It shouldn't. And is it cumulative? True. Yeah, it didn't give me an error. I'm going to do two things. Change that size to do it. Yes, that works. So this is what I put into the slide. Formula as well as the result. And 95th percentile for the previous distribution. So I'll just go back to there for now. We want the 95th percentile. Which means we want an inverse norm, right? Norm.IOV. Probability to the left, if it's the 95th percentile, what is the probability? What is area to the left from 95th percentile?
Five.
That's to the right. Remember, what does the 95th percentile mean? 95% less than that value. The mean is the same 100 and the same deviation. 15 divided by square root 36. This one doesn't work. Why does it not like this? Because I used the wrong bloody slash. Again, so used to my coding, I'm using the wrong slashes. I'll give you extra credit, you can solve that in 5 seconds. 5, 4, 3, 2, 1. Oh, bummer. Cool thing is there are people who can do it. With much bigger ones than that. I wonder if they have a Rubik's like polygon. Like, you know, the 20-sided die? Do a 20-sided Rubik's. If you can solve it, you're already ahead of me. I can't solve Rubik's. Can you save that one? So 104, 95% of all the means from sample size 36 are less than 104.11 or whatever. So do not forget the important points. First is when we can approximate the means as normal. When either the population is already normal, or if you're using sample sizes of at least 30. If you get, I ask you a question, or the population is not said to be normally distributed, and you have a sample size of less than 30, then the answer is this problem cannot be solved with these techniques. That's all you need to write. It can't be solved in this course or something along those lines. If one of those two conditions is satisfied, then you proceed with what we were doing today.
You said one of the two is okay.
Only one of those two needs to be satisfied. If it's normally distributed, it doesn't matter what the sample size is. If the sample size is 30 or larger, it doesn't matter if the population is normal or not.
As long as it says X is normal.
If X is normal, then the sample size doesn't matter.
Okay.
If the sample size is 30 or larger, it doesn't matter if it says X is normal. Right? X could be severely right skewed, but our sample size is 50. Then we can take the means to be normal. I do have it up there, the Unit 3 test, but we don't actually finish this unit until Thursday. I'm just putting it up there to let you know. So the Unit 3 test does cover M through R, which is everything with random variables. So that's, what did we cover? We did the discrete random variables, right? Then we did binomial distribution, standard, normal, and normal. Then the two central limit theorems, one for mean, and then proportion is Thursday. Answer this is my favorite. Actual inferential statistics, hypothesis testing. So I have a group work, but I also have the reference sheets that we have to use for the final to hand out. Ooh, that was good. You don't need to worry about the tables for the final because they will be provided with the final exam itself.